All right, today we're going to tackle something that sounds like science fiction, but it's happening all around us. How we taught computers to see. I mean, really see. It's an awesome story full of dead ends, huge aha moments, and a breakthrough that is literally changing, well, everything.
But to really appreciate just how big of a deal this is, we've got to go back to the beginning. We need to understand the problem that had computer scientists pulling their hair out for decades. Why was it so unbelievably hard to teach a machine to do something a toddler can do without even thinking?
I mean, think about it. You can spot a cat, right? Even if it's hiding behind a couch, or it's just a blurry photo, or it's hanging upside down from a tree. For you, for us, it's just instant. But for a computer, that same simple task was, for the longest time, basically impossible. So, what was the holdup?
Well, it turns out the early approach was, let's just say, super rigid. It was called pixel-wise matching. Imagine you have a perfect photo of a cat, like a stamp. The computer would take that stamp and slide it across a new image, pixel by painful pixel, looking for an absolutely perfect 100% match. If every single dot of color lined up, ding, 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 it found a cat. Yeah, you can probably already see where this is going, right?
So what happens if our cat in the new picture is just shifted a tiny bit to the left? Well, none of the pixels line up anymore. And to the computer, it's not a slightly moved cat, it's a completely different, unrecognizable blob of data. So, fail.
Okay, what if the cat is a little bigger because it's closer to the camera? The pixels are all wrong again. The whole arrangement is different. So that's another big fail.
And let's say the cat just tilts its head? You guessed it. All the pixels are in the wrong places. It's a total mismatch. This whole method was just way too fragile, way too brittle. It couldn't handle the real world, because the real world is messy, It's not a perfect grid of pixels.
So, yeah, this was a huge roadblock for a long, long time. We were stuck. But then came the breakthrough. And the inspiration for it wasn't a faster chip or a clever algorithm. It was us, the human brain. And this led to something called the convolutional neural network, or CNN for short.
And here's the absolute game-changing shift in thinking. Instead of looking for a perfect pixel-for-pixel match, CNNs do what we do. They learn to look for features, things like pointy ears, whiskers, a certain texture of fur. See, a CNN doesn't care if the pointy ears are in the top left or the bottom right of the image. It just cares that it found pointy ears. And that makes all the difference. It makes the system flexible, robust, a lot more like our own sight.
So what is a CNN really? It's a type of deep learning algorithm that's actually inspired by how our own visual cortex works in our brain. It learns to see in layers, building up from simple patterns to really complex objects. And this, right here, is the technology that finally cracked the code for computer vision.
Okay, so how does it actually do that? How does a bunch of code learn to spot pointy ears? Let's pop the hood and take a look. It's actually pretty cool. It's kind of like an assembly line for understanding a picture.
So it basically boils down to 4 main steps. First up is convolution. This is where the network uses these little virtual magnifying glasses, or filters, to scan the image and find basic stuff, like lines and edges. Then comes activation. This part decides, hey, is this edge important? Is it interesting? And passes the good stuff along. After that, we have pooling, which is all about summarizing. It kind of squints at the image and keeps only the most essential features, getting rid of the noise. And then the final step, classification. This is where it takes all those features it found, the pointy ears, the whiskers, the tail, and makes a final call, yup, all signs point to cat. And here's where the real magic happens. It's all about building up understanding, layer by layer. So, the very first layers, they're just learning super simple things. That's a line, that's a curve, that's a corner. But then the next layers take those simple pieces and put them together. Hey, a circle with a dot in it, that looks like an eye. Or a bunch of lines together, that's a wheel. And then the highest level layers take those shapes and assemble them into the final object, like a whole face or a complete car. It's learning to see exactly like we do, by putting together simple building blocks to understand a complex world.
Now, this all sounds great in theory, right? But this wasn't just some academic exercise. When these new CNNs were finally put to the test in a real competition, well, they didn't just do a little better. They absolutely obliterated the competition and kicked off a full-blown revolution.
And the main event, the ultimate proving ground, was something called the ImageNet Challenge. You can think of it as the Olympics for computer vision.
Teams from all over the world would compete to see whose algorithm could correctly identify objects in millions of different images. For years, progress was okay. It was slow, incremental.
And then came 2012. A CNN called AlexNet showed up. The winning error rate the year before was over 25%. AlexNet dropped it to just 15%. I mean, it didn't just beat the record, it completely shattered it. It was a total shock to the system. And that just opened the floodgates. In the next couple of years, you had new models like GoogleNet, then ResNet, each one making these incredible leaps, making the network smarter, deeper, and faster. The pace was just breathtaking. Then, in 2015, a model called ResNet hit an error rate of just 3.57%. Now, just look at that number for a second, 3.57%. Why is that so important? Because the estimated error rate for a human doing the same task is around 5%. So for the first time, a machine was officially better at this specific visual recognition task than we are. The revolution wasn't coming anymore, it was here.
Okay, so a computer can see, in some ways, even better than us. That's a huge technical achievement, for sure. But what does it actually mean for all of us? This is where the story really takes a turn from being about code and becomes about, well, everything.
There's a famous quote from Andrew Ng, who's one of the giants in this field. He said, "AI is the new electricity." And that's such a perfect way to put it. Think about how electricity changed everything a century ago: manufacturing, communication, daily life. AI, and especially these vision systems, is doing the exact same thing right now. It's not just a new app, it's becoming a fundamental part of our world. And honestly, you're seeing it everywhere, even if you don't realize it. CNNs are at the heart of medical scanners that can detect cancer in an X-ray, sometimes more accurately than a human radiologist. They're the eyes in self-driving cars, navigating complex city streets. They're what lets your phone unlock with your face. They're in security cameras, and they're what allow robots in a warehouse to see and grab the right box.
And this isn't just about massive companies either. This shift is creating brand new, incredible career paths. Take this quote from Andy Gallen, an AI engineer. He talks about how getting these skills was the single best investment he made, opening doors at a place like Tesla and doubling his compensation. It just goes to show you, understanding this stuff, it's like having a superpower in today's job market.
So we started this whole thing with a pretty simple question, right? How does a computer recognize a cat? And we ended up with a technology that is fundamentally reshaping our entire world. It was a long road to get there, but the result is one of the most powerful tools humanity has ever created. Which of course leaves us with the next big question. We taught them to see. What on earth are we going to teach them to understand next?